Hi, everyone. Welcome back to our next Geophysics and Tectonics seminar. Our speaker this week is Shawn Wei from Michigan State University, who'll be talking to us about compositional heterogeneities in the mid-mantle, revealed by seismic discontinuities and reflectors. So thank you very much for joining us, Shawn, and whenever you're ready.
Okay, thank you. Good morning, everyone. Thanks for coming, and also thank Kelly for inviting me to give this talk. And as you see, I'm going to talk about compositional heterogeneity in the mid-mantle, and mostly reviewed by, this is essentially the same seismic feature, I would say. That's basically the velocity and density contrast across in the mid-mantle. But if that's a more like a global phenomenon, I would tend to call it discontinuity. If that's a very localized regional feature, then I call it a seismic reflector. So first, I want to acknowledge my collaborators, Peter Scher from Scripps Institution of Oceanography, and Dongdong Tian, he's my postdoc at Michigan State University. And then also Minda Liu and his advisor, Suki Dorfman, they are mineral physicists in our department. They actually helped me a lot on one part of the talk today. And I also want to acknowledge Carolina Lisco-Bertonelli and Lars Institute from UCLA. They also helped me to a lot on another part of my talk today. So I first want to start with this cartoon. As I guess many of you have already read, this is a survey. This is a report from the National Academy of Sciences this year. They list I think more than 10 scientific priority questions in earth science. And this question is really interesting to me, is about the critical elements distributed and cycled in the earth. Then probably let's start from the mid-ocean ridge over here. Therefore, we usually have this melting differentiation. Then we have then therefore we will get the crustal materials containing certain elements versus the depleted mantle containing the other certain elements and also the minerals. And then when the lithosphere, this plates gets into the trench and then eventually brings some crustal materials down to the mid-mantle and then eventually to the lower mantle. And you see here, this is a question marker. We still don't know exactly the process over there. But then due to the mantle convection, some subductive materials will return to the mid-mantle and even return to the surface through mantle plumes. So this is the big picture of material recycling in our Earth. And for me as a seismologist, what interesting to me is that what can we learn from the compositional heterogeneity in this big picture of recycling, especially in mid-mantle. And here I want to talk about the mantle transition zone, especially the 410 discontinuity here, 660, and some structures above it and slightly beneath it. This is our topic around the mid-mantle. And so this is a good summary about the phase transition by Owen Doyce more than 10 years ago. And for a long time, people mostly focused on this olivine system, that we have olivine transition to Waziite, that's 410, and then to ringwoodite, this is the 520, and then finally to bridgemanite and ferropericlites, that's 660 discontinuity. And beyond, based on these diagrams that we seismologists use quite different a series of seismic techniques try to image these discontinuities. Here I'm just showing one example of receiver functions to image the 410 and 660 discontinuities. What's interesting, that's more than, well, nearly 20 years ago. What's interesting is that they find a strong correlation between the temperature in the mid-mantle and the thickness of the mantle transition zone. And then they got into this cartoon, which has been widely cited, widely used, is that in the hot regions, like mantle plume regions, that we should expect a thinner transition zone, and in the cold region, like around slabs, we should have a thicker transition zone. But we know that olivine is not the only mineral in the mantle. We also have, for example, another important mineral is garnet, and garnet transition will cause a series of other seismic reflectors or discontinuities that I will talk later. So things get more complicated than this simple cartoon model. And the technique I'm going to use today is called SS precursors. I try to use this diagram to explain to non-seismologists. Is that over here we have earthquakes on one side of the earth, we have seismic stations on the other side of the earth. And then once the seismic wave, here I'm just looking at S wave, starting from the earthquake and then reflected at surface and then going to the station. That is called SS wave. However, if we have a seismic discontinuity in the mantle like this one, then a small portion of energy will be reflected at the discontinuity and then eventually arrive at our station earlier than SS wave. That is called SDS or SS precursor. The advantage of this technique is that because these two phases sharing almost identical ray path, except that's right beneath the bounce point or the midpoint over here. So this is a very powerful technique to study the upper mantle or mid-mantle structure right beneath the bounce point, which can be in the middle of nowhere, because usually we have seismic stations on continents, earthquakes in trenches, but how about in the midpoint? So in this talk, I'm gonna mostly focus on a data set we compiled by my postdoc, Dongdong Tian. We, on this upper panel over here, all the red dots are the earthquakes since 1970s. And then because of this distribution of events and stations, and over in the lower panel, you see those red dots, those are our bouncing points over here. So those are basically just midpoints between station and events. Therefore, we have very good data coverage in Pacific Ocean and also in northern part of South America, and even in Indian Ocean, where we don't really have many seismic stations. So I consider this is a good technique to fill our data gap. But one problem for this SS precursor is that the signal is so weak. Therefore, we have to stack hundreds of these waves together. On left side here, I'm just showing one example. So this is stacked SS wave. That's a strong signal. And then over here, we see one peak that's actually a SS precursor reflected at 14 discontinuity. We call it S14S. And then we have another peak caused by 520 discontinuity and another one by 660 discontinuity. That's pretty much the focus today. And another thing I want to emphasize is that to be honest, I don't really trust the absolute amplitude very much, because the amplitude of these seismic signals are controlled not only by the velocity contrast across these discontinuities, but also controlled by say the topography of these discontinuities, but also controlled by the velocity in between in the upper mantle, and also the attenuation in the upper mantle. So there are a lot of complications to affect the absolute amplitude. And in this talk, I will mostly just focusing on relative amplitudes, like for example, the 520 amplitudes versus 410 amplitudes. And this technique actually has been used for a long time. This is more than 20 years. And here I'm just showing one classic paper and using the arrival time, and also to convert the arrival time of these phases to depth. So therefore we get depth of 410, 520, 660, and eventually get the thickness of the transition zone. Then we can use this cartoon to somehow tell us the story, the thermal structure of the mid-mantle. So that has been done a lot. But as you see from my title today, I will be more interested in compositional heterogeneity, and therefore I'm gonna look at something beyond the depth information. So again, I'm using this cartoon to show the first part of my the first case. Well, this is spoiler about water in the transition zone, and as you see here, that I will be focusing on the 14 discontinuity and some structure above it. So this is a well-cited cartoon summarized by Mark Hirschman more than 10 years ago, showing the Earth's deep water cycle, and then we know that the slab can bring water down to, well, some water down to even the lower mantle, and then some water will return to the mid-mantle or even surface. And what's interesting over here is that we know the water storage capacity in the transition zone is huge. However, this is just providing a glass. Either it's a glass of water or it's an empty glass. That's a big question. And then because of that, the estimation of water budget in the mantle, as you see here, varies a lot. Of course, this is probably outdated estimation, but still, we don't really know the exact water content in the mantle. So one big question over here is, what is the water content in the transition zone? Well, first of all, we want to find some direct evidence of hydrous mantle transition zones. On the left side, this is just one important paper published 6 years ago that was, I consider, one of the first piece of evidence of hydrous minerals that they find about 1% of water in this ringwoodite inclusion. And I believe there are some other papers following that, showing more natural samples of water coming from transition zone. But I will argue that those are just a handful of samples and can only represent a certain part of the transition zone. As a seismologist, we want to see if we can find more global scale or regional scale observations. This is the study I really like by Princeton group a couple of years ago, that they used attenuation image and find the higher attenuation in the transition zone. I believe this is beneath Europe. So that was one kind of I consider direct evidence of this possibly water brought down by slab. But however, the story gets more complicated. Here I'm just showing a few studies, and then people find seismic evidence of water. But also for this paper, I really like it. The take-home message to me is that the discontinuity topography and seismic velocity anomalies, these are usually the two major techniques people use to detect water. Unfortunately, they probably cannot very clearly conclusively detect the presence of water because of huge uncertainties and trade-offs. I believe this is still the cutting edge frontiers for many seismologists, for many geophysicists, that we still want to have direct evidence of water or not water in transition zone. But on the other hand, we probably have some indirect clues. This is also a widely cited hypothesis by Berkovich and Corrado. This is called transition zone water filter hypothesis. The very fundamental assumption behind this is that the transition zone has a lot of water because it has a high water storage. And then when water reached Waziites rise across this 14 discontinuity, the water storage capacity drops significantly, like this, and then water will be released as free water, and then will trigger hydrous melting, and therefore we expect a partial molten layer right above the 14 discontinuity. So in other words, if we can find this partial molten layer, or if we can find a low velocity layer above 14, maybe that's indirect evidence for water in the transition zone. Do we have this evidence? Yes. And on the left side, this I consider probably one of the very first discoveries of this low velocity layer above 410 discontinuity. And on the right side, this is our kind of incomplete summary of most previous publications of the detection of this low velocity layer above 410 worldwide. And as you see, these orange and red areas are all the previous detections. And then you might notice that most of these detections are kind of close to subduction zones. While there could be some bias due to the data coverage, but one leading hypothesis is that the water can be brought down, for example, like this by slabs, and then more water will trigger hydrous melting right above the 14 discontinuity. And this is another piece of indirect evidence suggesting that this is right beneath North America. And this is 660 discontinuity, much deeper than what I mentioned earlier. But then they find a strong negative signal over here that's indicating the partial melting caused by the mantle downwelling. And that is also related to the slab, Farallon slab at this uppermost lower mantle. So yeah, I guess generally speaking, we believe, yes, the mantle transition zone near the slabs is somehow hydrated. But to me, another interesting question is that, can we find such a low velocity layer in the middle of nowhere, which is not connected to plume, which is not connected to a slab? So I'm gonna use this as a precursor analysis to study our data set I showed earlier. That's a global data set. And over here, I'm just showing these waveforms again. We are focusing on SS wave, that's a reference wave reflected at surface, and this S410 as phase, which is reflected at 410 discontinuity. So ideally, because they are sharing almost identical ray path, therefore we are expecting very similar waveforms, except the amplitude. Like I said, I don't care amplitudes much. Then on this side, I'm showing the normalized waveforms. The blue curves are the SS wave reflected at surface, and the red curve is the SS precursor reflected at 410 discontinuity. So as you see over here, they are really just very similar, except that the noise level is higher for SS precursor. But that's one region over here. But in some other regions, we find this very strong trough over here. So that's for the observed SS precursor. So what causes that? We have done a lot of synthetic tests in seismology. And then on the left side, I'm showing you the blue curves are the density profile, and the red curves are the velocity profile. And dashed lines are the reference ISP91 model. So if we use this reference model, we will be able to produce a wave form like this blue curve. And it doesn't really have a negative trough. Only if we introduce this strong low velocity layer above 410, then finally we can get this negative trough. But I have to say there are a lot of trade-offs, so I cannot tell you exactly the thickness of this low velocity layer or the velocity contrast, because there's a strong trade-off. If you're interested, I can show you after this talk. But at least what we are confident is that as long as we can see this trough, that means we can. That means there must be a low velocity layer above 14 discontinuity. And we even introduced a new parameter called this RSR slope. It's basically the slope of this bar. And if this slope is negative, that means there's a significant trough in the seismic signature, and also means there's a higher possibility of a low velocity layer above 14 discontinuity. So let's try to apply this analysis on our global data set. On the left side, these are the circles are color-coded by this slope I just explained. The dark blue color indicates a higher possibility of a low velocity layer above 410, or if you want, you can interpret that as a partial molten layer right above 410 discontinuity. And the size of these circles indicate the confidence or data coverage in each region. So you probably can ignore those very small circles, and even ignore, of course, we ignore those blank regions. But over here, you can tell that we still see these blue circles in East Asia, in Pacific, and also in South America. That's indicating the existence of low velocity layer above 410. And let's zoom into Pacific Ocean, where we have better data coverage and with the higher resolution. Then interesting that we see these patches of blue circles indicating the strongly indicating the existence of this layer. In regions that we don't see this blue circle, for example, like these regions, I cannot exclude, I cannot say there's no such a layer at all, because possibly our resolution is limited. But anyhow, if we just look at this map, we find that the low velocity layer above 410 covers about 1/3 to a half of the resolved Pacific Ocean. And what causes that? Like we said, that could be hydrous melting right above the 410 discontinuity, and therefore that can indicate water in the mantle transition zone. And as far as I know, I don't think there's any slab in this region. The Hawaii mantle plume is over here, so there's no plume over here. What I want to say is that looks like we find hydrous mantle, region of hydrous mantle transition zone that is not directly fed by subduction or plumes. But you also definitely notice the strong heterogeneity over here. Why there's blue, strong blue colors here, but not other places. So we still are kind of puzzled by this strong heterogeneity that could suggest more complicated 410 dynamics, but also can indicate the varying water content in the mantle transition zone. So that's another. Hopefully, in the future we can solve that. We can have more independent observations to confirming our observation. Then I want to use this cartoon again to summarize this part of the case study. Is that we do find for this hydrous melting, we do find it is widespread globally, but it's not continuous like a cartoon model. Then let's move a little further down. So in the middle, in the middle of the mantle transition zone. And before I get into the seismic signatures, I want to just review a little about our understanding of mantle heterogeneity, mantle composition. This is, of course, probably an oversimplified understanding, but let's start from mid-ocean ridge, that if we have a paralytical composition, and then after melting, then we will have this basaltic crust. We have this depleted mantle represented by Haswigite. And then once this slab subducts into the deep mantle, we have this everything back again. The big question is what's the next? Whether do these materials mix again to reach a chemical equilibrium, like converting back to pyrrolite? This is one model on the left side. But alternatively, probably these materials never reach chemical equilibrium. And instead, we have this potting model that we have small pockets of either enriched or depleted materials in these small regions, small pockets. On the right side, this is a more, well, I would consider a more complicated model, is that we have a well-mixed mechanical mixture mantle that the red colors indicate basalts and the green colors indicate the depleted mantle. I'm not going to say which one is better, but what I want to try to stress over here is that we probably have a few end members. We have pyrrolite, we have Haswigite representing depleted mantle, we have basalts representing the crust, and we also possibly have this mechanical mixture model. Then let's see what are the seismic signatures of these end members of composition. So we first try to look at the more conventional idea of a pyrrolite, and then you see that by this is the simulation done by Hefesto, and then we will be able to see the 410 discontinuity, 520 660, we also see a small jump over here at about 800 kilometers. That's parallel. If we just look at Hasselblad, then olivine system is the dominating system over here. Then there's only 410, 520, 660. There's nothing beneath that. If we see use basalt, well, we know that's probably not a good model for mantle, but if we just look at basaltic composition, there's no 410, 520, 660. Instead, there's a strong garnet transition at the depth about this is 800 kilometers. Oh, by the way, so on the left side, this is the density profile. On the right side, this is the velocity profile. And the blue curves are our reference model, which is AK135. So, and this actually has been investigated a long time ago. And then she had proposed that if we just combine this Hasselblad and basalt together, we can have they call the mechanical mixture. And it looks like a mechanical mixture model with the basalt fraction of about 18% probably fits our seismic observation better than parallel composition. I don't know which is, I guess this is still under debate. There's different people have different preference, but what I want to stress over here is that by looking at seismic discontinuities and reflectors, we do get some clues of compositional heterogeneity, whether it's parallel Hasselblad or basalt. This is the motivation over here. So let's look at the mid-mantle. And this is the, so first we want to talk about the 520 discontinuity. So this is the classic paper by Peter Scheer 30 years ago. And what he discovered, besides 410 and 660 signals, there's also a peak over here. So that corresponds to 520 discontinuity because due to the transition from Waziite to Ringwoodite. What's more interesting is that 11 years later, Doyce and Woodhouse, they found that besides this 520 peak, they find another peak in certain regions. At that time, they call it split of 520, but here, just for consistency, I tend to call it 560 discontinuity. And on this right side, this is a work recently published on EPSL led by my postdoc, Dongdong Tian. So we basically summarize all the previously observed for 520 and 660 discontinuities globally. And as you see, the letters over here indicates different techniques. So there's a variety of seismic techniques used to detect these discontinuities. Here, what we want is try to use a more consistent, systematic way to do a global survey of this discontinuity. And here are just a few examples. I want to focus on two regions. One is over here. The other one is over here in the Pacific. So I want first to draw your attention to the lower row here. These are our observations. You can clearly see the signal for 660 and 410. And you also notice some signal in between. So how to isolate those signals? What we did is we calculated the synthetic seismic waves by assuming there's nothing between 410 and 660. Therefore, the synthetic waveform should look like this. And then we can calculate the difference, which is residual over here. So on the left side, you see this is very single peak, indicating 520 discontinuity. And on the right side, you see double peak. And that is 520 versus 560 discontinuities. And on the right side, I'm just showing this cross section from A to A prime. And then on the left panel, that is our observation. This is our synthetic waveforms. And then this is residual that we care. And from this certain waveforms, you can first see, for example, this is the 520 peak. And also in certain regions, you see double peak, that's 520 and 560 discontinuities. So let's just try to look at the global map. And here I'm showing the global map of the observation of 520 discontinuity and also the observation of the 560 discontinuity. the indicator here is actually relative amplitude of 520 versus 410, because like I said, I only trust the relative amplitudes. And the dark blue indicates a stronger signal of that discontinuity. So generally speaking, we observe this 520 discontinuity globally, almost everywhere. But for 560, it's interesting that we find blue dots in certain regions, like in subduction zones or in this beneath Pacific Ocean, where we have upwelling, mantle upwelling, and also in some other regions. And on the right side, I'm also showing the histogram of depth of these discontinuities. So I believe there are a lot of things to say about 520 discontinuity, that it's caused by ringwoodite transition to Wazite transition to ringwoodite. But what's more interesting to me is the 560 discontinuity. So we have done a lot of synthetic tests, seismic tests on the left side, and we find that at least we need 2% impedance contrast, velocity times density contrast, in order to create this 560 discontinuity. So what caused that impedance contrast is, well, this is a paper published more than 10 years ago by mineral physicists. They discovered that looks like the formation of calcium perovskite can cause that strong signal of 560 discontinuity. However, then this is the work done by Mingda Liu, our PhD student of mineral physics in our department. He discovered that if you just have a regular composition, then the formation of calcium perovskite is not sufficient to create such a strong signal, a seismic signal. Instead, we need at least 13% of calcium perovskite in that region of the mid-mantle to create such a strong signal of 560 discontinuity. So again, on this right side, therefore, I'm just wondering that maybe these blue dots can be served as indicators of localized calcium enrichment. And of course, next question is, how do we get this calcium enrichment? A straightforward guess is that due to the recycling of subducted crust. And therefore, we do see that these blue dots near the subduction zones and also near the upwelling regions. However, we don't really see a very strong geographic correlation. So if your, say, geochemical observation, if your geodynamic models also show this kind of patterns, please talk to me, and maybe we can further discuss the geological or mineralogical implications of this map, the existence of a 560 discontinuity. So again, I'm using this this cartoon to summarize my discovery over here, is that by looking at the 560 discontinuity, we actually identify some localized calcium enrichment in the mid-mantle. The last part of this talk, I want to look even deeper. That's beneath the 660 discontinuity. But here, I'm not going to talk about this hydrous melting. Instead, I try to look at some seismic reflectors deeper than in the lower mantle. So are there any seismic reflectors? The answer is certainly yes. This is a summary by Doyce again. So on these two maps, you can find seismic reflectors at different depths from 800 kilometers to 1200 kilometers worldwide. And then the conclusion at that time was that these reflectors are mostly related, associated with subduction zones. And then intuitively or straightforward, people suggest that probably these reflectors indicates some phase transitions or some other heterogeneity related to the subducting materials. So this is one story. However, a more recent study, like published 2 years ago, they reach almost the opposite conclusion, that on these two figures, maps, the colored dots indicate the detection of seismic reflectors at varying depths. And then they found that there are fewer seismic reflectors in the mid-mantle associated with slabs. I don't think I can tell which one is better, which one is reflecting the truth. And to be honest, I also did some similar global survey, but my understanding right now is it's not easy to tell because there's some difficulties in observation. For seismologists, there are a lot of interfering phases at those depths, therefore contaminating our seismic signal. It's not as clear as like 410 discontinuity. There's very few other interfering phases. And another difficulty is that in terms of interpretation, it is hard to interpret those reflectors because we generally believe there aren't many phase transitions in the lower mantle above D double prime layer. So what I want to do here is just to focus on a very localized region on this map because over the past 2 years, we have done a lot of synthetic tests. I'm very confident that this is not some signal artifacts. And on the left of this map, so this is Northeast Asia, this is Kamchatka Peninsula. Over here, this is the very northern part of Japan. This is the Russia. And what we find on the right side, this is a vertical cross section. We find the 410 discontinuity here. We find the 660 discontinuity here. But in certain regions over here, we also find a very strong reflector at the depth about 810 kilometers depth. And on the left side, these red circles indicate where the map view of our the detected reflector. So what is that? Then when I try to plot our observation against the tomography model, and so here I'm just the blue and red colors indicate the tomography model from Texas group last year. These dark stripes are our observation of 410 and 660, and this is our reflector at the 810 kilometers depth. And then you can also see this is the high velocity layer indicating Kamchatka slab. So interestingly, that you probably find, you can identify that this is reflected right above the slab surface. So is that the reason? Is that the cause of this reflector? Well, I will say every global tomography is the best. I don't want to discriminate them. So I try to plot our observation, these stripes on top of multiple tomography models. But interestingly, you'll find that depending on which model tomography model you are looking at, this reflector could be well above the slab, like this one, or right above the slab, like this one, this is a U-checked model. Then the question is whether what is the signal of what is the real geological meaning of this seismic reflector. So the first intuitive guess is that this is the surface of the thermal slab. And on the left side, I'm showing the cartoons from Foucault and Obayashi, and they use seismic tomography image the flat slab in Honshu and Century Curie, and then in Kamchatka. So if what we see is also the flat slab, we basically need to extend this lag of the slab a little bit further westward. But then when we try to look to do some synthetic calculations for seismic signals, on the left side, this is again the density profile and the velocity profile. On the right side, the red curves the red curve is our seismic observation. So you see two peaks. This is the peak corresponding to 660. This is the peak corresponding to 810 reflector. So in order to almost perfectly fit this second peak, we need to introduce a very high velocity zone that's possibly a slab at 8% velocity increase. That's a lot. Well, here I don't have much time to talk about some tricks behind this stacking. The idea is that because of the velocity heterogeneity in the upper mantle, because of attenuation, because of discontinuity topography, and sometimes we may overestimate this amplitude. So let's be a little conservative. But we assume the real amplitude of this signal is only like half of the observed amplitude. Still, we need about like 4% velocity increase to generate such a second peak. But this 4% velocity increase within about 5 kilometers depth has not ever been observed in any tomography models, and then it's also kind of difficult to be explained if you only consider thermal conduction. Another kind of tricky thing is here that if our interface, this reflector, has a VV topography, or if it has a deep angle, because we are stacking hundreds of waveforms together, then if this reflector has this complicated topography, then the amplitude of this signal will reduce a lot. But we do see such a strong signal, which also means that the reflector needs to be very smooth. It's not this wavy or dipping. Therefore, we are expecting a very smooth and horizontal and flat slab surface extending for at least about 1,000 kilometers. Is that real? Well, you always see this kind of flat slab in a cartoon, but I guess in the real Earth, in the real mantle, we never see such a very perfect slab. So therefore, we conclude the thermal lab interface is probably not the right way to explain our observation, this reflector. Then I want to bring this slide again, that's just to remind you that we have different end members of composition, because like I said, we conclude this reflector should be occurring at almost a constant depth. Then probably we really need to look at some phase transitions. So here we have 4 end members. We have perlites, Habsburgites, basalts, and mechanical mixture models. And let's see which model can produce such a strong signal at 810 kilometers depth. So we tried paralytic composition. Unfortunately, there's no such. So on the top panels, these are density and velocity profiles for each different composition. And the lower panels are the corresponding seismic signals, synthetic seismic signals. These profiles are calculated by Hephaestus. Then, so for paralytic composition, we don't see such a signal. For Habsburgite composition, we don't see such a signal either. That's not surprising. But for basaltic composition, yes, we see such a strong peak at about 800 kilometers depth. However, we know that our mantle is not purely basaltic. So let's assume mechanical mixture with the fraction of 18%. That's what Xu et al. Proposed more than 10 years ago. And we even try another kind of very large fraction value, which is 30%. We kind of get a little signal that comes from the Garnick transition contribution, but still that signal at 800 kilometers is not strong enough. Therefore, we think, well, by just looking at these conceptual end members, probably is not enough, is not good enough to explain our observation. So instead, we probably want to have a little bit more realistic model, still conceptual model, is that we have a subducted slab crust, we have subducted depleted mantle, we have ambient paralytical mantle over here. And then we have these 4 different thermal profiles. And let's see what's the density and the velocity profile just right across this flat slab. So that's what's showing over here is the density profile versus the velocity profile. The the black curves are our reference model, which is AK135. And then you do see some Garnick transition. If I shift this flat slab at the right position, it needs some practice, and then possibly we can get this Garnick transition. But even so, if we try to calculate the synthetic waveform, we don't really see any signal at about 800 kilometers. That's because the velocity transition over here is not velocity contrast over here is not only the Garnick transition, but also the transition from mantle to crust and then to mantle again. So there are a lot of complexities over here. Well, unfortunately, we still cannot explain our observation. But how about that we assume the crust is much thicker? The thickness is about 35 kilometers, which is typical for an oceanic plateau. And then, yes, suddenly we can get this strong seismic signal at about 810 kilometers depth. And I want to say this signal comes not only from Garnick transition, but also the transition from this mantle to crust and crust to slab mantle. So all of these together can contribute to this seismic signal of the 510 reflector. What's more interesting is that if I just zoom in this part, this is the density profile, you might find that the density profile of our slab actually crosses the reference density profile. So, well, of course, we need to consider a lot of dynamics, consider a lot of other complexities, but it at least gives us a potential that the slab, or at least the slab crust, could be neutrally buoyant at this depth. That means this slab could possibly stay at this depth for a long period of time, and also means that because this is a phase, so the reflector is relatively smooth and flat. So now I think this is still a hard conclusion to reach, but we have rule out all other possibilities. I believe the only possible explanation for this reflector is an thickened oceanic plateau in the uppermost lower mantle at the depth of about 800 kilometers depth. Now, okay, I'm showing that we have an oceanic plateau in the lower mantle. Why do we have that? It's not common in the lower mantle. So this is a classic paper more than 20 years ago, summarizing the large igneous provinces globally, including oceanic plateaus. And then the leading hypothesis is that when mantle plume rises up to the surface, the plume head will generate a large amount of decompression or melting, and then a large amount of magma to create large igneous provinces. And beyond, from that point, and people try to link all the existing plumes to all the existing large igneous provinces. For example, over here, this is Deccan Trap, and people try to link that to the Reunion mantle plume. And well, I guess this one is widely accepted model. But when we talk about plume, of course, the first thing we need to think about is Hawaii. And I believe this is the first ever piece of evidence that Jason Morgan used to propose the hypothesis of mantle plume. Now we have this very nice Hawaiian emperor Simon Chen that tells us the history of Hawaiian plume from the current state to the past. But my question is, where is the oceanic plateau that was generated by this Hawaiian plume? Well, it probably has already been gone into the trench. So when we look at this current plate motion, as well as the plate reconstruction models, we find interesting that everything about this Hawaiian plume older than this is 80 million years should have already subducted into the Kamchatka Trench along this direction. And that's exactly where we find this oceanic plateau. So over here on left side, I'm showing this, the red circles indicate our observation of the oceanic plateau over here. And on the right side, I'm just showing one possible history of the Hawaiian, the oceanic plateau created by Hawaiian mantle plume. It's just one possible. There could be, there needs to be more plate reconstruction modeling to verify that, or we need more independent observations. But so what we assume over here is like 100 million years ago, we have this Izanagi plate, this is Pacific plate, this is the Hawaiian plume over here created a large igneous province. one part is on the Izanagi, one part is on Pacific. And then over years, so as you see, Izanagi part of the plateau subducted into the Aleutian Trench long time ago. But let me see, this is the Pacific part of the plateau finally reached the Pacific, the Kamchatka Trench and then subducted. And these are the snapshots of the animation I showed earlier. But you may notice that there's still some discrepancies in regarding the current position of this plateau. Looks like we have this plateau subducted much earlier and then much deeper. But then we believe probably that's there's uncertainties in terms of the initial location of this Izanagi Pacific Ridge at the very beginning, and also uncertainties for plate motions. So, but again, I want to say this is just one possible models of plate reconstruction. But what we are confident is that we do see an oceanic plateau that is in the lower mantle, and the most straightforward, simplest explanation is that it was caused by created by the Hawaiian mantle plume. And I want to use this cartoon to summarize my talk today. So earlier during the talk, I started from 410 and then getting deeper. But now for the summary, I want to go from the other direction, that we know the slabs are bringing materials down to deep earth, and then that's how we have an oceanic plateau in the lower mantle, and we have this garnic transition in the lower mantle, and then subducting materials will return to the mid mantle to form these localized calcium enrichment regions. And also water will be brought back to the mid mantle and then eventually cross this 14 discontinuity to trigger hydrous melting right above the 14 discontinuity. So I will start over here, and thank you very much.
Thank you very much. I'll applaud for everyone. That was wonderful. Are there any questions for Shawn?
I have a question. Shawn, that was a great talk. This is Ed. Do you have good azimuthal coverage of the underside reflections of the 810 structure you were just talking about? Because I was wondering if azimuthally you see it more strongly from some corridor than another, which might imply non-planar structure.
That's a very good question. And that's actually the reason we spent additional 1 or 2 years to verify this. Yes, we do see a strong kind of azimuthal anisotropy. Well, is that called anisotropy or dependence over here? Is that for a certain region, for example, this cap, we do see this 810 reflector in certain azimuthal direction, but not in another one. However, just if we move a little bit further away from here, we basically see this reflector in both directions. And this actually really raised us concern, because whether this is real, we spend a lot of effort to confirming this is the structure right beneath the bouncing point, not because bias due to stations or near station structure or near source structure. And but because we have seen these reflectors in multiple caps in multiple different azimuths, so we believe that's a real case. But I'm very intrigued by this azimuthal dependence. But unfortunately, the short answer is we don't have that strong, good enough resolution, because in order to see so, we need to stack hundreds of waveforms. But if we just want to see one azimuth direction, we don't have enough seismograms to stack. And also because we are stacking such a large region, so it's hard to tell whether that comes from the lateral heterogeneity or the real azimuthal coverage. And so I guess this is still an open question, and ideally we can install some stations over there and using, for example, receiver function, which has a better resolution to image this this reflector. Sorry.
Okay, cool. Thank you.
Thank you, Ed. Kent Condi, is that a question or just a comment?
Just a comment, but this problem of where the oceanic plateau was associated with the Hawaiian hotspot, you've made the first case, I think, for documenting where it might be, and you made an excellent case to support that.
Thank you. Well, to me, it was not that easy to make this conclusion, but like I said, we ruled out all other possibilities. Then this is probably the only reasonable explanation.
Thank you. Jeroen Ritsema, you have your hand up. Thank you.
Hi, Shawn. That was great. I like that a lot. I couldn't quite figure out why, what constrains the thickness of that plateau to be 35 kilometers? What is it in the observations that, yeah, make you?
Okay, that's good. So the short answer is that's just a guess. So this is probably, I can make it a little bit larger. And we tried that classic like 6 kilometers crust, and then we don't see this signal. And then we tried this is actually 20 kilometers thickness of that oceanic plateau. We do see some signal. So the reason we use 35 is simply because that's the thickness of Ontan-Java thickness, Ontan-Java plateau thickness. So we consider this probably a typical thickness. What I mean is that, yes, we can also possibly see this signature if the oceanic plateau is only 20 kilometers, but the signal will be weaker. Yeah, well, I should
Sorry, but you are relying on the amplitude then of that signal. Is that correct?
Yes.
Okay. But
not absolute. Yeah, not precisely. But I just want to see whether it's strong enough. If what's clear here is that 6 kilometers is definitely not strong enough. But maybe 20 is probably okay, and 35 is good enough. Is what we prefer.
Okay. Thanks.
Thank you. Kian Yuan.
Yes, yeah, thank you, Kelly. Hi, Shawn. Nice to meet you. A great talk. Yeah, I really enjoyed know much about the detail of the upper mantle structures. So I have a question for the slide 16 about you have maybe 3 different components for the possible composition for the mantle. So yeah, I would agree it's very reasonable to use pyrrolite as the composition for the mantle in the upper part. But is that possible in the lower mantle? It's better to use a different component. So because 810 is already in the lower mantle, so there are possible more different materials coming.
Yeah, sure. That's why we tried different compositions, and but because the black curve is AK135, which is a global 1D model, and what you can see here is that it matches the pyrrolite composition prediction fairly well. So I think, and also this is the paper by Xu et al. More than 10 years ago. So I think either pyrrolite or this mechanical mixture model can reasonably explain the general picture of the lower mantle. What we are looking at is a very regional, is a very localized region west of Kamchatka. So therefore, for that small region, probably we have more basalt. In some other regions, we probably have more depleted mantle. But generally speaking, for the entire lower mantle, I still think this pyrrolite model or this mechanical mixture model is a good representation of the global lower mantle.
Okay.
Does that answer your question?
Yes, but I think in the lower mantle, the mineral change to bridgemite, and also the mineralogy is totally different from upper mantle. So I don't know if the major composition is still similar to the. Okay.
Oh, here I'm just talking about the chemical composition, and certainly there are mineral transitions over here. That's why this kink actually corresponds to garnet transition in perlite.
Okay.
And Hasselblad doesn't have garnet, so that's why you don't see any kink over here. And the mob has basalt has a lot of garnet, so you see this transition over here. What I showing here is, well, this should be paralytic composition, and this, like for example, on the right side, down to 800 kilometers, it's definitely not basalt anymore. It's some rocks with the same chemical composition of basalt, but with the completely different mineral structures.
Okay. Yeah. Thank you, Shawn. Great talk.
Thank you. There's another question in the chat from the Chen. One, I will read them out. There are also positive signals other than the 520 and 560, especially above 410. How do you explain them?
So yeah, that's a good question. That's why. Let me see if I have any getting into the weed of seismology, and so, well, unfortunately here I don't show many phases, but you probably get the sense that when we try to use this as precursor to map seismic signals, that we are mainly just looking at these three curves. That's 410, 660, and 520, 660 discontinuities. But in addition to that, there are also a lot of different seismic phases with the completely different move-outs. So therefore, usually we have to limit our epicentral distance range to try to minimize the contamination from other seismic phases. And then, for example, sometimes, let me see over here. So yes, we do see some signals above 410, and then this is actually even beneath 660. But we believe so. Well, I cannot say none of those is true, but I guess some of those are caused by interfering seismic phases. But certainly that's an interesting that's a topic we can do, is that trying to look at either discontinuities or reflectors. And actually there were a lot of publications before trying to look at upper mantle discontinuities, like called X discontinuity, or even shallower discontinuities, possibly. But here our focus is just 410 and 60. Sorry, it's just 520 and 560.
Okay, and then there was a second question, which is, what do you think causes the flattening of the slab around the 800 kilometers depth? And is the oceanic plateau not causing slab flattening at shallower depths?
So well, that's just my guess, because this is observation. We see what it is. But my guess here is this hint that maybe because this density profiles crosses the reference profile, that means potentially slab can be neutrally buoyant at this depth. However, if we consider the entire mantle convection dynamics, consider other driving forces, probably this is not the case. I guess the answer is I don't know why slab is flat here. Well, you probably know there are other studies suggesting there's a viscosity change at the depth of 1,000 kilometers, and then that's possibly can be another reason. Or maybe it's always flat and sinking. This is the snapshot we see currently. But unfortunately, I don't know the answer. I just see this is what's happening now. Well, Kelly knows better from a modeling perspective.
I was going to say you would probably have to model it, but it would depend on a lot of things. So it's interesting to see the seismic observations. There's a question from Jackie Lee.
Yeah, sure. Thank you for the talk. I have a question about actually using these pages. My question is that I noticed that there is a velocity jump in this oceanic plateau. I wonder if this jump is caused by the phase transition for the basalt or something else.
Yeah. So this jump, you are talking about this jump, right?
Yes.
Yeah. This jump is actually exactly caused by garnet transition in the basalt, in the basaltic crust. This is garnet transition
and
here.
Actually, this velocity jump that caused the signal we observed in the waveform, right?
Not only in this one. This probably is one of the major contribution, but also you need to consider the velocity reduction from mantle to this crust over here across this slab interface, and also the velocity increase, velocity jump across this slab mantle. So what I'm showing here is I basically consider all of those three contrasts together. That's how we get this signal.
Okay.
Yes, garnet transition is probably one of the most important factor, but I believe also this slab mantle velocity jump is also important.
Okay. And I have another question, which is if the temperature fell something or some composition changes, if in this narrow depth range, the garnet is already transformed to another phase, so there won't be this kind of phase transition interface.
So here is, as you see, this yellow to red curves. Those are just thermal profiles. This I consider wide range of potential temperatures. I believe that's probably wide enough to capture all possible thermal conditions. And then you see that no matter what kind of thermal profile, we always have this same contrast and also the same seismic signal over here.
Okay, thanks a lot.
Thank you. Wenbo Wu, you had a question?
Yeah, I had a question, but I think I should take it back because you saw two discontinuities. What I thought about is, how about just accumulated basalt, which have very small scale, and then they just accumulated there. We would say some, for long period, it looks like a flat discontinuity. But yeah, if we use short period waves, they look like scattering. But you say, yeah, two discontinuities, that will be very hard to accumulate basalt here, and yeah.
And also maybe the lowest cartoon is related to what you ask over here. Is well, it's possible that we have a orphan crust over here. That's not exactly what you imagine, but of course this is oversimplified cartoon. The answer is we cannot tell which one is better. Maybe the slab crust detached from the downgoing slab, and then we have, like you said, accumulated the crust in the uppermost lower mantle, and then the rest of slab going down, and we still get the similar signature over here. So yeah, this is possibly a good explanation, but we just think, well, from seismic tomography or from just simplicity, we think maybe the earlier model with the combined slab is probably easier interpretation, but either way can work.
Yeah. What I said is actually it's the original oceanic crust is just 6 kilometers, but here the conversions in the mantle makes them fragmented and then accumulated here. So the original thickness is still 6 kilometers, but the accumulation makes them thicker and thicker and thicker.
Thicker. That's a good point. Well, then you need to, well, then I guess I need to talk with geodynamic modelers to see is that possible to accumulate that bunch of, and why at this depth? Well, it's a good question.
Yeah, the depth is I think because they are buoyant, but the top discontinuity, it's very hard. How can we get this also relatively, it's seen by the SS precursors. Yeah, we can talk about it later. Yeah.
Yeah, but definitely, I hope in the future we will have different seismic techniques with higher resolution, like receiver function, like SCS vibration, those things, to look at this same place. SS precursor, I guess, this is the first step we do, but I hope they are following work.
Yeah, very nice talk. Yeah.
Mm-hmm.
Thank you. And we have one other question
hey,
in the chat.
Shawn.
Guliang,
please go ahead.
I think I guess the oceanic crust here is less dense than the subducting slab and also less dense than the lower mantle. So during the subducting process, do you think the oceanic crust will detach from the subducting slab, and they maybe not keep their shape around the 800 depth? Do you think that is possible? Yeah, what I mean is that
definitely it's definitely possible. And but like I said, this is what we observe, and we do observe something at 800 kilometers depth. And as shown in the lower cartoon, that could be it's complete. The slab is completely detected. I even probably can cut this part off. So this is often oceanic plateau. It's totally reasonable. And I believe like a lot of modelers like Peter Van Kerken, more than 20 years ago, they modeled that the oceanic crust at under certain conditions can detach from the downgoing slab mantle. Yeah, it's possible.
Okay, that's maybe the oceanic crust not only detached from the subducting slab, they also scattered and become the very small pieces in the mantle. So yeah, if that case,
we consider that. Yes, we do consider that possibility. Like, then that becomes another like mechanical mixture model. Well, regional scale mechanical mixture model. But then we thought a little about the geodynamics, and we believe within this is only like a few tens of millions of years. Within that time scale, it's unlikely to break oceanic crust into that small pieces and then evenly distributed in the lower mantle. It's kind of hard, but yeah, maybe we need to look at more numerical simulations.
Okay, thank you. I really like your talk. Thank you.
Can I?
Yeah.
Yes. Oh, first of all, congratulations on the publication of a science paper. That's super awesome and cool. And I'm so happy that and lucky we have a great colleague like you who can teach me more. And please come to my group meetings and teach us. I'm totally teachable. All my grad students and also postdocs, they are teachable too. And also I put some of the this link for the Mantle.io team, right? It is for offline asynchronous discussion. I used for my class, CMS C201, it's computational modeling to methodology based on like Python. So the idea is that, I created this team for you guys to join in. It's not a spam, yeah. It is a platform for offline discussion, for in-depth discussion, and you can create questions. If you have any question, you go there and ask the question, start this discussion. Anybody can contribute to the answers, okay? And then you can vote the answers up and down, and also to find it if it's inspiring or not, disagree or not, agree, but with your arguments. So there is AI, like artificial intelligence, network analysis and machine learning behind this platform will help you to decide who you agree with more, how far your thought process or distance from the others, and also the connection, the interaction between each other, and also identify the potential collaborators. So it's a fantastic software platform for you to use. I paid for this platform out of my own pocket. So don't worry, it's not a spam. I'm not selling this product for anybody else. However, I do think it's the best way for us to, get to the truth, right? Through fair and equal discussion. What do you think?
Sure.
I will
yeah,
send
I will
out,
check.
yeah, to the listserv. It's a good way to continue this discussion offline and asynchronously, especially for our colleagues and collaborators on the other side of the Pacific who are probably not watching this live since it's the middle of the night. So this way they can continue to have discussions with you. So thank you very much, Min Chen, for setting that up. And I'll make sure that the rest of the listserv gets access to it if they'd like to join and chat. And let's just, before it gets any later, I just want to thank Shawn again for joining us and for the wonderful talk and great discussion. So thank you, Shawn.
Thank you all. Thank you, Katie. Bye.